morning. I came in a little bit late, but it's because they forced me to dance. Just want to say, first of all, Bob has my infinite respect, and that's like infinite, like universal infinite, not 1 inch. Although we've been known over the years, people would see us back in the day when I used to drink or whatever, we would sit around in the bars yelling at each other till like 4 in the morning. But he's, I want to give Bob credit because part of the SpaceX Elon Musk plan basically came out of Bob. And I'm paying you a compliment, dude. What do you want? Oh, okay. I was like, anyway. So our next speaker is also somebody I have immense respect for. And actually somebody who actually stays within his time, unlike Bob and I. Although Bob did great. And look, Phil Metzger, Dr. Phil, as I like to call him, which he doesn't like to be called, is with the University of Central Florida. He was the founder of the KSC, Kennedy Space Center SwampWorks, one of their most creative hubs for NASA. Dozens, if not hundreds of papers that he's published. And his range of activities, even though he is astrophysicist, correct? Planetary scientist is amazing. He goes from robotics and inspiring kids to being one of the greatest experts on asteroids in the planet. So Phil, it's all yours.
Thank you.
Oh, I should tell since it is.
You can take that. Real quick.
I want to also thank Phil because Phil has been with us basically from the beginning with Earthlight, New Worlds, with these conferences, has done an incredible job. So we're glad to have him here.
Thank you, Rick. I've got a mic here. So that was an awesome talk that Bob Zubrin just gave us. I'm going to switch gears here. He was talking about Mars. Mars is freedom. I'm going to talk about why we are returning to the moon right now. Now, I'm an all of the above person. I'm not just a moon person, so I love Mars too. Now, right now, NASA has a program, the Artemis program, and people have asked the question, why are we spending time going back to the moon again? We've already been to the moon. The Apollo program left footprints, it left flags, it brought back rocks. The moon is boring. Why do we want to go back to the moon? So I'm going to give you 3 answers to that question, why I think the moon is an amazing place for NASA to explore right now. First of all, science. We did science in Apollo, but the science that we did raised questions that are really important, and we know we cannot answer those questions until we get astronauts back on the surface of the moon. For example, since I was in graduate school, the leading theory on the formation of the moon has become the giant impact hypothesis. We believe a planet the size of Mars impacted the Earth about 4.5 billion years ago. We even gave it a name. We call it Theia. Theia was the Titan who was the mother of Selene, which is the moon goddess. And so Theia, we believe, formed somewhere different than the Earth, a little further out from the sun maybe. It migrated, it collided, and it looks something like this. Most of Theia absorbed into the Earth, which we think may have given Earth an extra large core, which possibly helps explain why the Earth's core is still molten and creates a magnetic field, which is important to maintaining the atmosphere and advanced life here on the surface of our planet. So understanding the formation of the moon may give us insight into the habitability of other planets for advanced life. But some of Theia, a smaller fraction, went into orbit around the Earth, and the impact blew some of the Earth into orbit, and the mixture of the two formed the moon. But the ratio of the amount of Theia material on the crust of the Earth should be lower than the amount of Theia material that is in the moon. And so the chemistry of the Earth and the moon ought to be different. They formed at different distances from the sun. The isotopic ratios ought to be different. But the Apollo program showed that the chemistry of the Earth and the moon are actually pretty much the same. And this argues against the impact hypothesis. And there are people that don't believe the impact hypothesis. Most do. So a couple of years ago, Sarah Stewart at UC Davis came up with a new hypothesis. She calls this a synestia, which is, she pointed out that when a planet impacts the Earth, it's going to vaporize a lot of rocky material and create a big vapor cloud, which would be donut-shaped, and the moon and this crust of the Earth re-solidified inside the same plasma cloud. And this could cause the chemistry to be evened out between the two planetary bodies. But did this really happen? In order to study this, we need to get back to the moon. We need to get samples from the Earth, from the moon's mantle. And the place to do that is in the South Pole Aitken Basin of the moon. It's the deepest impact crater in the solar system, and it excavated almost to the mantle. So there should be a lot more basaltic mantle material available in that part of the moon, which we've never explored before. And there are other things we can do as well to study the internal structure and therefore the formation of the moon. But not just the formation of the moon. By returning to the moon, we're going to study the formation of the entire solar system. See, what we think happened was the proto-sun was condensing. It began to burn, and as the planets were forming, the radiation pressure drove the volatile elements out of the inner solar system, and they didn't condense until beyond the frost line, which is outside of the asteroid belt. And that's why the giant planets are so far out, because they got the volatiles. But then the question comes, well, how did the Earth get oceans? How did we get carbon for our bodies? Because those should have been blown away from the inner solar system, and the Earth and Mars should not have had these elements. Well, that led to this idea that something happened in the solar system that brought the volatiles back in. And during the Apollo program, we got samples from the rays of some of the big impact craters, and we dated those rocks. And we also look at the crater counts, the different terrains in the solar system. We noticed that the shape of the crater distribution is different on the older terrain than it is on the younger terrain. And this led to the hypothesis that there was a late heavy bombardment in our solar system. Something disrupted the solar system, caused lots of comets and or asteroids to swarm in and bombard the Earth, the Moon, and Mars, bringing water and carbon, and that's why they are life-supporting planets. But did this really happen? It's been questioned recently, was there really a late heavy bombardment or something like it? Well, this is the study that was done by a group of scientists recently. They met in Nice, France, and so the model is called the Nice model. This is a map of the solar system. It only shows the giant planets. So you have the sun, and then the red one is Jupiter, and then Saturn, and then what comes next? This map has Neptune and then Uranus, so they're backwards. And the model says perhaps they used to be backwards. But then this is what happened in a simulation. The gravity drag of the Kuiper belt, all those small objects, caused Neptune to spiral in. It got into resonance with Jupiter, which kicked Saturn out, and Saturn then kicked Neptune out, and Neptune flew out, plunged into the Kuiper belt, disrupted it. So the modern Kuiper belt is the remnant, and it's further out than it used to be. But about 10% of those icy bodies are shown by the simulations to have swarmed into the inner solar system and may have bombarded us, bringing the carbon and the nitrogen and the water and all the other things we need for life. Now, did this really happen? If it did, it would be important to understand this so that we could say how many other star systems have something similar, and therefore is intelligent life abundant in the cosmos or not? Really fundamental question to answer this. But how do we get data about the bombardment history of the inner solar system from billions of years ago? The problem is, here on the Earth, we have weathering, we have the rains, we have plate tectonics, which destroys all the evidence. And so people have pointed out that the moon is Earth's attic. This is where our family history is stored. So we have to climb up to the attic to get the evidence. Now, we started doing this in Apollo. We took core samples of the soil. We could see the layers, the many, many strata in the soil. And we thought we could start to unravel the impact history because every layer in the soil is an impact ejecta blanket. But it was too complicated. The moon is just craters on craters on craters. Small craters, big craters, and it was too complicated to sort it out. And we realized to sort it out, there are certain kinds of data we need to get, but we need to get back to the moon to get it. We need to get samples from a wider variety of impact events. We need to dig horizontal trenches in the soil to study how these impact ejecta blankets change over distance, how they taper, and how the particle sizing changes over distance so that we can sort it all out. Now, NASA has been developing robots to do trenching on the moon. This is in the SwampWorks. This is the Razor robot, and you can see it makes nice vertical sidewalls in the trenches because the cohesion in lunar soil, including simulated lunar soil, is so high you can get nice vertical trenches. And so we have the ability to go back and sort out the solar system's history to understand deep questions about life in the cosmos. Now, not just the impact history itself, but also some of the materials that came in that impact history are really crucial to our science. This is a map of the amount of sunlight at the south pole of the moon averaged over an entire year. And you can see there are some areas that never get sunlight at all throughout the year. We call those permanently shadowed craters or permanently shadowed regions. And this is a temperature map that was measured from orbit using a radiometer. And the temperature in those craters is about 40 degrees above absolute zero. So cold that any water molecules that wander into those craters will never come out again. And so they build up over hundreds of millions to billions of years. But the question is, where did that ice come from? So in 2009, NASA crashed the LCRAFT spacecraft into one of these craters. It blew out about 5 tons of material. We had 2 other spacecraft watching it, and they measured that the impact ejecta wasn't just mineral grains, it was also a large fraction of ice. And it wasn't just water, it was also methane, ammonia, hydrogen, carbon dioxide, other simple organic molecules. And the measurements showed that it's fine-grained crystalline ice mixed in with the soil. The current theory is that hundreds of millions to billions of years ago, maybe multiple times, large asteroids or comets hit the moon, created a temporary atmosphere, a fraction of it froze into these craters, creating ice sheets. But then subsequent impacts broke up the ice sheets and into finer particles and mixed it into the soil. But we want to know, where did these impactors come from? What part of the solar system gave us that ice? Was it asteroids, wet asteroids, or was it comets from further out? Was it interplanetary dust, which is mostly carbonaceous, which has clays that have water in it? Or was it solar wind forming water on the surface of the moon, or a combination of them? So we need to get physical samples from the moon to do chemical analysis and isotopic analysis to understand where did the ice come from, which tells us about the history of our solar system. And we need to get it from multiple locations around the poles of the moon and to drill it at different depths to really unravel this complex history. But this ice that's on the moon leads us to a second reason we want to go back to the moon, because the ice isn't there just for science. We can use it as a resource. We can turn it into rocket fuel. Now, I've done economic modeling of mining the moon and making it into rocket fuel because there are skeptics. People say that you can't outcompete launching it from the Earth using Starship, for example, as it lowers the launch cost. So I've done recent modeling. I have a 45-page manuscript in review at a journal, but I've already had it peer-reviewed on my own by 5 leading economists and business executives in the space industry. And this paper, I believe, is totally rock solid. So I'm going to show you the economics of the ice from the moon. Now, currently, when you launch a spacecraft off the Earth to go to geosynchronous orbit, it'll initially start out in geostationary transfer orbit. This is not to scale, of course. But it's a highly elliptical orbit. And then the spacecraft will use a small electric thruster, which is very efficient, to slowly raise the perigee until it reaches a circular orbit, at which point it can start servicing customers. But this process takes 6 to 12 months. During that time, the spacecraft owners are paying all costs on the spacecraft. Operations, finance costs for building it, everything, and the spacecraft is degrading in the space environment. The technology is getting behind. So they lose about $100 million in revenue during that time while they're paying all the costs. But this is the cheapest way to do it. But the new paradigm is this. You make rocket fuel on the moon. You launch a tank full of it on a space tug, and a single tank will do this. We've done all the analysis. So you launch a space tug off the moon with a tank of gas. It rendezvous, maybe you use aerobraking, you don't need to, but use aerobraking to drop into GTO and rendezvous with that spacecraft. And then in just one day, you can boost it to its final orbit, and that recovers. Oh, and then the space tug returns to the moon to refuel and do it again. Now this recovers $100 million in revenue per boost. So if you can do this for less than $100 million per boost, you have a business case. Now I've done the economic modeling. When you manipulate the equations, there in that bottom line there is a Greek letter phi. That phi is the ratio of rocket propellant you produce per mass of capital. So it's a mass ratio. And the modeling shows if that number is about 35 or higher, then you are able to outcompete anything launched off the Earth. So this is using baseline parameters for actual techno-economic analyses of lunar mining. And the lower axis is the distance from low Earth orbit. 0 is low Earth orbit. 6250, this is measured in delta V, meters per second. 6250 is the lunar south pole. You can see where geostationary transfer orbit is, that vertical line labeled GTO. The vertical axis is years after the start of your mining operation. And so using standard, very conservative assumptions, even if launch cost drops to crazy low values, the launch cost, you can launch water cheaper, but you can also launch the capital cheaper. And so using very standard conservative assumptions, lunar propellant outcompetes Earth launch propellant, and it gets better year by year, so that eventually, even in low Earth orbit, lunar water is cheaper than Earth launched. So the problem is, how do you afford the startup system? How do you convince investors to put enough money into this? Because it is risky, it's a new thing, and it does take a while to perfect the technology. So I invented a method of extracting the ice from the moon. I don't have time to go through it. It's a starter system. The analysis of that system shows that within a couple of years, you can outcompete Earth-launched water in geostationary transfer orbit, and the entire system fits on a single small lunar lander. So with a small initial investment, you can start business, start to make a profit. It doesn't scale well, so you never outcompete low Earth orbit, but then you want to switch to a different mining method. And this is a method that was innovated by George Sowers, who was the chief scientist at United Launch Alliance. He's now with the Colorado School of Mines, using large tents, the heat under the tent to sublimate the ice. And the analysis of this system shows that even from year one, your value of phi is about 15 times higher than it needs to be to outcompete all the way to low Earth orbit. So there's really no question that no matter how cheap launch costs get, the moon will always outcompete the Earth for making rocket fuel. Now, one of my people that I asked to review this pointed out that SpaceX, with the Starship, is going to have a glut of launch capacity. And even though it's more expensive to launch it from the Earth, they may want to do that anyways, because they want the launch business. But in the long run, if you want to settle Mars, that doesn't make sense, because if it will take about one Starship to launch a payload and then 8 more Starships to refuel it in low Earth orbit to go to Mars. But if you refuel using lunar propellant, the total cost, even if the lunar propellant costs the same as launching from the Earth, we're not out competing, just saying they're the same cost, then it'll still cost the same per payload, but SpaceX Capital is sending 9 times more payloads to Mars, so you get 9 times the value. You speed up the settlement of Mars by a factor of 9, and the investment costs of building a city on Mars with compounding interest is drastically reduced. So the moon really can contribute to settling Mars. I can share the slides later if anybody wants that. Okay, and the reason number 3 that NASA is returning to the moon is preparation for Mars. Now, people have said SpaceX doesn't need to get bogged down on the moon, they can go straight to Mars. I agree. If it makes business sense for them to do it that way, they can do it that way. But what I really mean is so that NASA can contribute to Mars missions. See, the problem is NASA has a certain way of doing business which is dictated by the political world, and it's not that efficient. Charlie Bolden said a couple of years ago that NASA does not get enough budget to do Mars missions. NASA has to change the game somehow. And cislunar economy is one of the ways to change the game. But even in the near term, even as you're developing that cislunar economy, there are things NASA can do on the moon which will make Mars missions better and faster and cheaper. For one thing, you can develop the dust-tolerant technologies that we need. You can develop the mining and the resource processing. Most of those technologies are transferable. Not all, but the majority of those technologies are transferable from the moon to Mars. Robotics and artificial intelligence, that's going to be more important on Mars so that we can have the ability to control spacecraft from the Earth. They're going to need more autonomy. Well, the moon is the place to do that, where you have a short time delay. You can get astronauts there to fix the hardware and iterate rapidly. Hardware reliability is the big one. Getting that value of phi high enough to make economics, the lunar water economics profitable. You need to have a low failure rate to keep phi low enough, to keep the massive spares low enough. And the moon is the place to perfect the reliability for mining and resource processing because it's so close. And the time delay is so small. And NASA can afford to be there. NASA cannot currently afford to be on Mars. And then experience operating in a harsh planetary surface environment. There's operational issues that need to get worked out. And then, as I mentioned in the previous point, cislunar infrastructure to improve the economics in cislunar space. So there you have 3 reasons. Why return to the moon? Because some of the most amazing science accessible to humanity is actually right there on the moon. There's also great science on Mars. But let's not forget the science that we can do on the moon, which will be amazing. There's also a revolution that we can have in cislunar economics through propellant mining and manufacturing, which has geopolitical implications, by the way. And then thirdly, because this will be a pathway for NASA to develop capabilities that will enable human missions to Mars. So I am super excited about the Artemis program. We have been to the moon before, but Artemis is not Apollo. It's going to be better, and this time we're going to the moon to stay. Thank you so much for your attention.